Welcome back. So we're talking about vector calculus, namely the gradient, divergence, and curl operators, and how we can use those to derive partial differential equations and encapsulate kind of physics into equations. So I want to start today by really just zooming into these operations of div, grad, and curl. And in particular, this all starts with this kind of del or nabla operator. It depends on how old-fashioned you want to get. This kind of Greek delta symbol, I guess upside down delta. So del or nabla. And this is literally defined as a kind of vector of partial derivatives. So we're going to think about taking the derivative of something as an operator or an operation. And so if you want, you could put a little arrow over this. Sometimes I do, sometimes I don't. I'll do it right now. But if I drop this arrow, it always means the same thing, this del or nabla operator. These are the same word for two words for the same thing. And this is literally, let's say we have a three-dimensional del operator. This is going to be partial x in the I direction plus partial y in the j direction plus in the k direction, we're going to have partial z or z. Okay, I just learned that Americans pronounce z as z because it rhymes in the ABCs. A, B, C, D, E, F, G, blah, 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 rhymes with z, not z. Everyone else in the world calls it z. So this is the del or the nabla operator. And another way to write it is as a vector, and then we can take the dot product or the cross product of that vector with other vectors. So this could also be written equally as del equals the partial x, partial y, partial z or z vector. And if I took this and dotted it with another vector, it would take partial x of that first component plus partial y of that second component plus partial z of that third component. This can be treated like a vector. And if you like, this I hat, kind of I hat, j hat, and k hat just refer to the first, second, and third components of my vector. Just like if I had a vector v and I called it a, b, and c, that would be the same as a in the I direction, b in the j direction, and c in the k direction. And I could draw this in coordinates in my I, j, k coordinates. I could draw this vector as I take a steps in the I direction, b steps in the j direction, and c steps in the k direction. And that would determine my vector v. Okay, so I just want to just demystify anything here. If you have an I, j, and k out front, you can write it as a sum like this in these unit vector directions. You can write it as a column vector like this, where it's assumed that the first component is in the x or I direction, the second component is in the y or j direction, and the third component is in the z, z, or k direction. Just like any other normal vector you would ever write, totally fine. Okay? Good. And this grad operator, so del or nabla, sometimes this is also called grad. Maybe I'll put it up there. This is also the gradient or the grad operator. It is a linear operator, and I'll tell you kind of how to compute the grad, the div, and the curl in a minute. So I don't know what the history of del versus nabla is. Yeah, nabla, the funky Homo sapien, would sound a little weird, or like nablatron 3030. So okay, let's look at these operators. So the gradient operator, maybe I'll switch colors here. So the grad operator essentially takes a scalar field f and it turns it into a vector field. Okay, so it takes a scalar f and it returns a vector field. And it does it in the following way. So if I have grad of f, and little f is, let's say f is a function of x and y and z or z, okay? Then grad of f is just partial f partial x, partial f partial y, partial f partial z in a vector. And for every point in space, there will be literally a vector direction with these partial derivatives determining that vector. Okay, that's what the gradient does, is it computes the rate of change of f in the x direction, y direction, and z direction. Good. And we already showed that you can think of this as like the gradient of a temperature distribution. It will tell you in what direction the temperature is rising the fastest. That's what the gradient of the temperature would do. It would give you a vector direction at every point of how that temperature is increasing the fastest, along what direction. The divergence, and I'm just going to alternate colors so it's easy to see. The divergence takes a vector f, let's call this vector f, and it returns a scalar field. So it's kind of the almost exact opposite. So if I take the divergence, it's literally defined as the dot product of my del operator, my nabla operator, with my vector valued f function. And we assume that this vector f has three components: f1 in the I direction, f2 in the j direction, and f3 in the k direction. And all of those f's are functions. So this would equal, maybe I'll write it up here. So vector f is literally f1 in the I direction plus f2 in the j direction plus f3 in the k direction, where each of these f's is a function of x, y, and z in 3 dimensions. Then this divergence is going to be partial, okay, I'll write it out because it's going to get ugly. It's partial partial x, partial partial y, partial partial z, that's del, dotted with f1, f2, f3. Okay? That's what del dot f is. It's literally taking this operator and dotting it with my function f. And so we know how to take the dot product. This is easy. It's just the partial of f1 with respect to x. It's partial f1 partial x plus partial f2 partial y plus partial f3 partial z. Okay? Pretty simple. It's just a sum. And now, because we've summed this up, this is just a scalar function of x, y, and z. So it took my vector field and it returned a scalar field. And specifically, it's going to compute how much my vector field is kind of instantaneously or locally expanding outward or contracting inward. So this divergence is going to be greater than 0 if my vector field is kind of sourcing out, blowing stuff away from a point. And it's going to be negative if it's pulling stuff in or kind of attracting stuff in into the vector field. And a divergence-free vector field, a vector field where this is equal to 0, is called incompressible. And it literally means incompressible in a fluid dynamics sense. OK, the last one I want to show you is the curl. And the curl is also kind of cool. So the curl takes a vector f, and it returns a vector field. Okay, so all of these are a little different. The grad takes a scalar and returns a vector. The div takes a vector and returns a scalar. And the curl takes a vector and returns a vector. Same f as before. And literally the curl is just nabla, or del, cross product with my f function. Okay? Now, kind of a mess. I don't really want to do this, but I'm going to. Remember how to take the cross product? It's pretty easy. You take literally the determinant of a matrix where you have the I, j, k directions, and then you have the vector representation of del here, which is partial partial x, partial partial y, partial partial z, and then the vector representation of f1, f2, f3, and you literally just compute its determinant, And it's not that bad. I'll write it out. In the I direction, you have I times partial f3 partial y minus partial f2 partial z, minus in the j direction, you have partial f3 partial x, minus partial f1 partial z, and then plus in the k direction, you have, I guess, partial f2 partial x minus partial f1 partial y. So again, you can tell that this is a vector field because it has an I, a j, and a k component. And the curl, roughly speaking, maybe I'll draw a picture for the divergence. The divergence, of course, measures how much stuff is kind of sourcing out from a point. The curl is going to measure how much stuff is kind of swirling around in a circle. It measures kind of the circulation around a point like this. Okay, so a positive curl means we're rotating around. Positive divergence means we're kind of expanding out. And the gradient, of course, measures if I have like a temperature distribution from hotter to colder, it's going to give me directions where I maximally go from cold to hot. Okay, so really, really simple. This is like the alphabet. These are the building blocks of vector calculus. It's all based on taking the derivatives of things and measuring rates of change. Remember, we love calculus because we can measure how things change in space and in time. That's how we think about differential equations. That's how we think about partial differential equations, is how things change in space and in time. These are the building blocks that we're going to use to quantify things like conservation laws to derive these partial differential equations. So in the next few lectures, I'm going to go into great detail. We're going to zoom into the gradient operator and get physical intuition for what this means and how to compute it. Same thing with divergence, same thing with curl. And then we're going to start deriving our vector calculus kind of integral formulas like Gauss's divergence theorem and Stokes's theorem, how these behave under integrals. Really cool stuff, and especially when I learned it, there was no motivation for why we were learning it. We just had math on a board. You are learning this specifically so that you can translate physics, the language of the universe, into math, the language of differential equations. All right, more to come. Thank you.